Okay, let's kick it up a notch. Let's take the same block of charge, but instead of having a uniform charge density, let's give it a charge density which depends on how far away you are from the center. So let's say that our charge density is 1 minus z, your vertical position, divided by the total distance. So where you are depends on, or the amount of charge density you have depends on where you are. So let's start this problem more or less the same as we did for the problem with the uniform charge density, but when it comes time to calculate our charge inside our Gaussian surface, we're going to have to be really careful with how we calculate that charge. So we know we're going to use Gauss's law. Gauss's law states that the net electric flux is the integral of E dot dA equals Q enclosed divided by epsilon naught. So Gauss's law refers to the net flux through a closed surface and the amount of charge within that surface. So we should draw our Gaussian surfaces. So I'm going to say that we'll use the same shape of a Gaussian surface, which is going to be a box with a thickness between minus z and plus z, centered at z equals 0, with a cross-sectional area of A. So I'm going to draw my box of charge. There's my z equals 0 line, and remember this is the front-on version. You could draw it 3D if you wish, but it gets a little bit complicated to draw. So my z-axis is going up. So if we're inside, my Gaussian surface is going to be a block inside my block of charge. So there's my Gaussian surface. It's a box. It's got cross-sectional area A. So that's the area of the top face if we were drawing this in 3D. The thickness is from minus z to plus z, and it is centered at z equals 0. Okay, so that's my Gaussian surface if we're inside. My Gaussian surface if we're outside looks pretty much the same, except for the Gaussian surface is going to extend outside the edges of the box. Okay, it still has a height of z. What else can we put on here? We might put the thickness of the box on here. So this is A, and this is A. Your height above, from here to here, that's Z, and below would be at minus Z. Okay, so where we're going to go from here is let's deal with the first term of our Gauss's law. Let's do the integral of E dot dA. I'll go through this one a bit quickly because we took our time with it in the last example and it hasn't changed since then. So first let's draw our electric field lines where we have positive charge. The electric field lines are going to go out from the center. There's no curving here at the edges because it's an infinite block of charge. There are no edges. So the electric field vectors are going straight out. Let's do our integral of E dot dA next. So integral of E dot dA gives us our net flux. We have to do it for every surface on our box. For the top surface of our box, the dA points straight up. And let's get a label in on our electric field vectors. Those are the ones in bright green. So straight up on the top for our Gaussian surface inside, straight up from the top for our Gaussian surface on the outside. So this is true for either geometry. Integral of E dot dA is the magnitude of E times the magnitude of dA times the cosine of the angle between them, which is 0. E is constant when we're a constant distance away. So we're E outside the integral of dA times the cosine of 0, which is just 1. Integral of dA is A. Okay, bottom face of our Gaussian surface. There our dA points straight down and straight down, regardless of whether we're inside or outside. So the bottom is same as top. Integral of E dot dA equals EA. Okay, the sides. On this side, the area vector points to the right. This side, it points to the left. The front points straight out towards me, back points back away from me. So all of those dA vectors on the sides, those are all perpendicular to the area vectors. So the integral of E dot dA for the sides is magnitude of E times magnitude of dA times the cosine of 90 degrees. Cosine of 90 is 0, so this gives us 0. That tells us that our net electric flux is EA plus EA plus 0 equals 0. Okay, equals 2EA. So what we've got done so far then is this side of Gauss's law. Now we have to deal with this side, and we have to sort out how much charge is inside our Gaussian surface. This part is going to be a little bit more challenging. We did this in an example with a sphere with a variable charge density. We're going to apply the same strategy here, but it's tricky because the charge density is not uniform. There's lots of charge here at the center, but there's not so much out at the perimeter. So we have to account for the fact that the charge changes. So that's going to be our next thing to attack. Get a fresh sheet of paper. So we're going to ask, what is Q inside? What is our Q enclosed by our Gaussian surface? And we'll start with when we're inside. So when Z is less than A. I'm going to draw my box again and my Gaussian surface. There's my box. There's my Z equals 0. There's my Z system, my Z axis. Here's my Gaussian surface. Okay, let's build on that idea that we used for that sphere with non-uniform charge density. What I can do if we have a non-uniform charge density is I could take however much charge is on this slice of my Gaussian surface. I could add it to however much charge is on this slice, add it to this one, and this one, and this one, and this one, and this one. If I add up the charge on each of those little slices, I'm going to get the total charge on the top half of my Gaussian surface. And I'm just looking at the top half because things are funny. Z's allowed to be negative, but my charge always has to be positive. Everything on the top is positive, so I'm going to figure that out, and then to get my total charge, I'll multiply by 2. Okay, so when I have a non-uniform charge density, I'm going to add up, and remember, when I'm adding up a whole bunch of things, it means I'm going to do the integral. So I'm going to add up each small bit of charge, and a small bit of charge we call dq, and it's the small bit of charge that's on each small slice, or each small portion, or each small fraction, whatever you like to say. And the amount of charge it's going to be on each small slice is dq. It's going to be the density, wherever that slice is, times the volume of that small slice. Okay, so the little bit of charge is going to be the density times the volume. That's going to get the net charge on the top half of my Gaussian surface. Total charge on the top half, I'm going to call Q for the top. Then I'm going to double to get the net charge on my Gaussian surface. The notation I use for the net charge enclosed by the Gaussian surface is Q enclosed. Okay, hopefully that strategy is clear. So normally we identify one small such area. So we'll call this chi dq. That little bit of volume we've identified has volume dv. So my Q for my top half is the sum of all those little dq's. Each little dq can be found by doing density times volume. It's only a little slice, so it has a little volume dv. Okay, first thing we're going to figure out is how do we say what dv is. dv is the volume of this little slice, and remember this is a three-dimensional object. The volume is going to be area times thickness. Area part's easy. We said our Gaussian surface had a cross-sectional area of A. Thickness is a little bit in the z direction. Now, this density has a z in it. This is our z coordinate system. That has a thickness of z. I feel like we're going to get tangled up in z's, so I'm going to call this thickness here dz primed, because I'm also calling this distance from here to here z, and I don't want to get tangled up in all my z's to get confused. So my thickness I'm going to call dz primed so I don't get confused between this z and this z. Okay, so the next thing I'm going to do is I'm going to put in my expression for my density. There's my expression for density right here. Equals integral of rho naught, that's a constant, times 1 minus the absolute value of z over a times dz primed. Now this is your coordinate where you are. So this is z primed. That's the location of that slice. So that's z primed. Again, trying to be really careful that I don't get tangled between this z and all the other z's. So we don't want to get confused there. Now here we have something that simplifies. I decided I was just going to find the charge on the top half. I don't have to fuss about doing the integral of an absolute value. If I'm only doing the top half, my z is positive anyway. I can drop my absolute value signs. Because doing integrals of absolute values can get a little bit tangly. Okay, this is looking a little more pleasant. Let's put in the limits of our integral next. We're trying to find the amount of charge on the top half. My top half starts at z equals 0, z primed equals 0, and it stops when z primed equals z. So now to do my integral, I suppose I'll break this up into two integrals. The first one is from 0 to z of rho naught times 1 times a times dz primed. Then I'm subtracting the integral from 0 to z of rho naught times z primed over a times dz primed. Okay, this is a bit of a hassle to write down, but it's not truly a difficult integral to do. Let's keep going. So this first one, I can take my constants out front, rho naught a 0 to z dz primed, minus, I can take my constants out front, rho naught a over a 0 to z primed dz primed. Okay, let's just deal with this integral part next so I'm not writing down a million things. Integral of dz primed is just z primed evaluated at z and 0, which is going to be z minus 0 equals z. Oops, sorry, I said z and I wrote 0. And then my next one, this is equal to z primed squared over 2. It's evaluated at z and 0, so that's going to be z squared over 2 minus 0 squared over 2 equals z squared over 2. Okay, this is going in here, this is going in here. You can leave it like this if you wish, or you can take your rho naught AZ outside. I think maybe not. I will do that. Rho naught AZ outside of 1 minus Z over 2A. Okay, this is our net charge enclosed by the top half of our Gaussian surface. To get the total charge on our Gaussian surface, we're going to have to take the top and multiply it by 2. So my Q enclosed is the charge enclosed by the whole Gaussian surface is 2 times the charge on the top, equals 2 rho naught AZ 1 minus Z over 2A. Okay, now let's put our answers together in our Gauss's law expression. In our Gauss's law expression, we've got net electric flux is the integral of E dot dA equals Q enclosed over epsilon naught. Remember, we're inside now. So our integral of E dot dA, we said that that was equal to 2 times EA. We figured that out from the geometry. 2EA equals. And then we did a lot of hard integral work to find that this was the charge enclosed by our Gaussian surface, equals 2 rho naught AZ 1 minus Z over 2A. We're trying to solve for the electric field. Got a 2 here and a 2 here, A here, A here. So then our electric field is equal to rho naught Z 1 minus Z over 2A. This, of course, is a vector, so the direction of the vector is straight out from the plane, and we can put a K hat on that to tell us it's straight out. Or you could write it in words to say it's straight out from the plane. Okay, there's inside. Next, let's do outside. So let's start fresh a little bit. So for outside, that's for Z greater than A. Let's redraw our block of charge. Let's redraw our Gaussian surface. Okay, so we're going to apply the same strategy that we did for inside. The only difference is the limits of our integral. Now to find our net charge, we're going to add this bit to this bit to this bit to this bit to this bit, and then we're going to stop here because there's no charge right here. So the Q on the top half is going to be the integral of dQ, adding up the charge from each little slice that each has volume dV. So that's rho times dV. dV is the area of each little slice, rho times A times dZ primed. So each little slice is located at Z primed, and each little slice has thickness dZ primed. Let's see what goes in here. We'll put in our expression for rho, which is rho naught outside of 1 minus. Now our rho naught has the absolute value. We're staying on the top half for right now, so we can just leave off the absolute value because our Z is positive anyway, times A times dZ primed. The limits of our integral, we want to cover the entire top half now, so we're going from Z primed equals 0 to the value at the surface, which is Z primed equals A. Okay, so we can follow this integral through the same way. So this is equal to the integral of rho naught A dZ primed from 0 to A minus the integral from 0 to A of rho naught Z primed over A times A dZ primed. And then that's going to boil down to rho naught times A times the total thickness of the plane minus rho naught times A over A times a squared over 2. I won't go through all those steps again. I'm sure it's pretty boring to watch. This simplifies a little bit this time. So a squared over a. If you're not sure about those steps, you can just go back and follow through what we did here. Instead of the upper limit being z, though, that upper limit is a. So this is rho naught times a minus rho naught a over 2 equals rho naught a over 2. So there's our net charge enclosed in the top half of our Gaussian surface. Next, we'll find the net charge enclosed by the Gaussian surface. So Q enclosed is our symbol for the total charge enclosed by the Gaussian surface. It's going to be twice this much, or twice this value. So rho naught a. Now we'll put our Gauss's law back together. Gauss's law says that the net electric flux is the integral of E dot dA equals Q enclosed over epsilon naught. Integral of E dot dA we saw was 2 times E times A. Q enclosed is rho naught A over epsilon naught. Let's see what cancels this time. Only our A cancels this time. And then our electric field is equal to rho naught A over 2 epsilon naught. This is a vector, of course, and the direction is straight outwards. Okay, so there's your electric field around a plane with non-uniform charge density.